let's talk about chemistry. I know we all love chemistry, right? Anyway. So the main process through which biodiesel is made is called the transesterification process. Now, transesterification process is where the alkoxy group of an ester and the alkoxy group of methanol are exchanged, or alcohol. And the alkoxy group is literally, it's shorthanded for car. And the alkoxy group is just a combination of like hydrogen and carbon molecules. So in the biodiesel reaction, the main ester that we're going to use is called triglycerides. Now, triglycerides can come in any form. They're typically oils. And for our purposes, since this is alternative energy things, we focus on the waste vegetable oil because we want to reuse what we've thrown away. So as you can see here, this is the chemical equation of the triglycerides. And these little squiggly lines right here are the alkoxy groups, which we'll shorthand as R. So the alcohol that we use in our reaction is methanol. And here's a chemical equation for that, a 3D visualization of what the methanol molecule looks like. Now, methanol and oil typically don't want to combine, so you usually have to implement a catalyst. You can either use sodium hydroxide or potassium hydroxide. But in our case, we use potassium hydroxide because it doesn't need to be stirred to dissolve. So it is presented in a pellet flake form. This is an actual picture of the flakes that we had for our potassium hydroxide. So biodiesel, to make it, you have to heat up the feedstock, and we were going to heat it up between 104 to 122 degrees because that's what our materials can withstand. Because we don't want to go any higher than that, we might face melting issues. The methoxide and the triglycerides will react, and then biodiesel usually settles at the top because it has lower density, and glycerol settles to the bottom because it has higher density. Now, this is actually the chemical equation for what the biodiesel reaction looks like. So we have our triglycerides with our alkoxy group right here, and then our methanol. We add the catalyst, and we get biodiesel with the alkoxy groups, and then glycerol. So the biodiesel reaction, the basic cooking formula for it is there's about a 1-to-1 ratio for biodiesel created and feedstock needed to create it. And then there's a 1/4 ratio of methanol needed for every one feedstock you have, and then a 1/50th ratio of catalyst. Due to the densities, like I said, it separates very nicely. It's like syrup and water, kind of. So the main purpose behind this project is we weren't just making biodiesel, we were making it in a continuous flow form. So the main function through which the continuous form works is by the angle in which you angle the reactor. Now, when that comes into play, the settling velocities of the different chemicals come into play, and they can be represented by this equation. And this is basically what it looks like, a visualization of what that process looks like. Now, before we could actually make biodiesel, we had to make methoxide, which is where we didn't take the methanol and the feedstock and combine them together. We made methoxide first with the catalyst infused into it, and then threw that in with the oil. So this is what methoxide looks like. It's an extremely dangerous chemical, and that's why safety was very adamant about making sure we covered our bases. And it's an organic salt, an extremely strong base, and can harm you if you touch it. So the methoxide, like I said, is created by taking methanol and combining it with potassium hydroxide. There's a ratio of 2 to 25 for every potassium hydroxide to methanol you need to add it in there. And the potassium hydroxide has to be mixed into the methanol and not the other way around. If you mix it the other way around, it might blow. So that's fine. Now Gabriel Potowski is going to go ahead and talk about our test mixing of the methoxide.
To fill with the methanol, I used a pipette to fill the beaker with 100 milliliters of methanol. We then also placed a magnetic stirrer in there, which would later be used to mix the potassium hydroxide into the methanol. I'll cover that a little bit later on. We had 8 milliliters of potassium hydroxide, and those conversions to English units are 0.026 gallons for the methanol, as well as 0.575 ounces for the potassium hydroxide. The reason why we have 2 separate units here on this slide is because the equipment used in the chemistry lab is an SI unit, so then had to use the conversion to the English unit system. That's why we're showing 2 separate units.